Ladies and gentlemen, good morning everyone. Assalamu alaikum wa rahmatullah. It's my great honor and privilege to welcome you all today to today's conference. We are here to explore one of humanity's most profound questions. Are we alone in the universe? In our search for answers, we have been fortunate to have brilliant minds lead the way. Today, we are privileged to be joined by one of those pioneers, Professor Geoffrey Mársi. Geoffrey Mársi currently serves as the Director of Space Laser Awareness, an organization focused on developing technology to detect lasers emission from space, which can be used for communication and detecting extraterrestrial signals. Professor Geoffrey Mársi has an impressive academic record with more than 700 published papers and over 60,000 citations, reflecting the profound impact of his research on the field of astronomy. Geoffrey Mársi co-discovered over 100 exoplanets during his career, including some of the first exoplanets ever identified and the first planet orbiting the Sun-like star 51 Pegasi b. In fact, Geoffrey Mársi and his collaborator Paul Bulter confirmed the discovery of 51 Pegasi b just a few weeks after its initial announcement by Michel Mayor and Didier Queloz in 1995. Mársi's confirmation helped validate the groundbreaking discovery, which was the first detection of an exoplanet orbiting a sun-like star. Geoffrey Mársi, often referred to as Mr. Exoplanet, has traveled over 10,000 kilometers, crossing the Atlantic and North Africa from California to Algeria to share his vast knowledge with universities across the country, including here in Bátnة. So as we begin today's conference, let's be inspired by the incredible possibilities ahead. And now I give a speech to the Dean of Science of Matter faculty.
السلام عليكم. مرحبا بالجميع في هذا اللقاء العلمي. أولاً أرحب بالسيد البروفيسور عبد السلام ضيف مدير جامعة باتنة واحد بحضور هذا اليوم العلمي، وكذلك أرحب بنواب المدير وكذلك عمداء الكليات ومدراء المعاهد، رؤساء الهيئات العلمية، رؤساء الأقسام، الأساتذة، الضيوف الكرام، الطلبة الذين قدموا من مختلف كليات ومعاهد جامعة باتنة واحد، بالإضافة إلى تلاميذ ثانوية مالك بن نبي. نرحب بهم في هذا اللقاء الذي سيقدم إضافة في مشوارهم العلمي. أخص كذلك الترحيب بالبروفيسور جيفري مارسي الذي قدم إلينا من كاليفورنيا، كان أستاذ سابق في جامعة كاليفورنيا والآن راه مدير معهد الليزر الفضائي. نرحب به في رحاب جامعة باتنة واحد، وهذا شرف لنا عظيم أن يحضر قامة علمية الذي ساهم في اكتشاف الفضاء وطرح عدة أسئلة حول الحياة الذكية في الكون، إضافة إلى مشواره العلمي الذي توج بنشر أكثر من 700 مقال علمي والتي منها مقالات منشورة في المجلة العريقة والعلمية المعروفة ساينس، بالإضافة إلى مجلات أخرى. كذلك يتمتع الأستاذ جيفري مارسي بدي سيتاسيون، استشهادات كثيرة، أكثر من 60,000 استشهاد، وأش إندكس أكثر من 100 أش لانديس دويرش. إذن هو قامة علمية سيقدم إضافة بالنسبة لجامعة باتنة واحد. نرحب به ونتمنى له إقامة سعيدة وشيقة واكتشاف لمدينة باتنة. You are welcome, Mr. Professor Jeffrey Marcy.
I give a speech to the rector of the university, Professor Kepler.
بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين، السادة نواب المدير، السادة عمداء الكليات ومدراء المعاهد، الأستاذات الفضليات والأساتذة الأفاضل، رؤساء الهيئات العلمية، الطالبات العزيزات والطلبة الأعزاء، مرحبا بكم جميعا في هذا اللقاء العلمي المميز والمتميز بحضور البروفيسور الذي شرف لنا أن نستقبله بجامعتنا، ولعلنا نستفيد من ما سيلقيه على مسامعنا من خلال مداخلته التي أعدها لهذا اللقاء. أيضا الشكر موصول للأخ بوزيدة عبد الله صاحب مؤسستي مالك بن نبي وابن رشد لمشاركتهم لنا وحضور التلاميذ والتلميذات، لعلهم أيضا يحتكوا بالجامعة ويعرفوا الجامعة عن قرب، وأيضا يحضروا ليستمعوا إلى ما سيدلي به الأستاذ الفاضل من مداخلة في الموضوع. وقد قدمه السيد عميد كلية علوم المادة في كلمته قبلي، أن قدم الرجل وما يملكه من إنجازات علمية كبيرة. شرف كبير لا تتاح لنا دائما الفرص أن نلتقي مع مثل هذه القامات. وأشكر الأستاذة حمانة ورا أشكرها جزيل الشكر، لأن أبلغني العميد باللي هي اللي كانت الواسطة لكي يحضر معنا، وقد وافقنا وفرحنا بأن يكون بيننا. لا أطيل عليكم، نتمنى لكم أن تستفيدوا وأن تستمعوا لما سيقوله هذا الأستاذ الفاضل، وأيضا أتمنى أن تتفاعلوا معه من خلال أسئلتكم وإبداء ملاحظتكم، وهنا تكون الفائدة. شكرا لكم جميعا على كرم الإصغاء، وباسمكم جميعا أعلن عن افتتاح هذا اللقاء. وليتفضل البروفيسور. Hello, welcome.
Now I give the floor to Professor Jeffrey Marcy.
Can you hear me in the back? Okay. I will speak in English. I hope that's okay. First, I would like to say how honored I am to be here. I am very happy to be here. This is a wonderful experience being at the Bhatna University. I'm very happy to be talking to all of you. It is my honor. I am very deeply happy to see you and to meet you and to give you some ideas about the research that we are doing. So thank you for being here. Today I will talk about some research that is very recent. We are beginning to discover planets that are similar to the Earth, perhaps planets that can have life on them. And we're beginning to ask questions and do observations to determine if there is intelligent life in the universe. So I will be telling you about current research in both of these topics that are, of course, related to each other. The question you might ask yourself, even if you are a young child, is how common are Earth-like planets? And we don't know the answer, but we are beginning to learn. And of course, the Earth is special. The Earth is the only place in the universe where we have detected biology. It's the only place where we have found life. So you might wonder if there are other Earth-like planets and whether they have the conditions, the environmental conditions for biology. Now, the way we detect Earth-sized planets is very simple, and I would like to show you how we detect those planets. What we do is we watch the star. And what happens is a planet crosses in front of the star like that. And as the planet crosses in front of the star, the planet blocks some of the starlight. So the brightness of the star dims. And what we measure is the dimming of the star. And of course, as the planet goes around the star, it blocks the starlight, goes around, blocks the starlight, goes around. And so we have a prediction about when the starlight will be dimmed because we know how periodic, how regular, how predictable the orbit of the planet is. This is just like a light bulb that has a bug, an insect, land on the light bulb. The room will dim, and you will know that a bug landed on the light bulb because of the dimming of the light. You don't see the bug, but you can see the dimming. Similarly, we do not see the planet, but we see the star dim over and over and over. So that's the technique. Very simple. Now, the problem is you need to measure the brightness of a star over and over and over to see the dimming. So we had to develop a telescope, a special telescope, and we wanted to put that telescope in space. So I would like to show you the telescope and the launch of the telescope from Florida. We actually brought the telescope to Florida, and then we tried to launch it. Don't start it quite yet. So I brought, can you hear me in the back? Yes. Wow.
You must listen.
So I have two videos of the launch. Okay. I have two videos of the launch of the telescope. And I would like to ask which of the two you would like to see. One video is a home video that we took with just a regular camera. So that's just a regular home video of the launch of the telescope. And I also have the official NASA video of the launch. So which one second one. Yeah. Oh, the sound isn't coming out.
There's no sound.
Oh, okay. This is without sound.
It's repeating.
That's good. Can we go back to that? So the launch was successful, and the telescope went into space. And now I will show you the data, the actual brightness measurements that we got from that telescope in space. It's a special telescope designed simply to detect planets the size of the Earth. And you see here the field of view. It is, get my laser pointer, oh no, this is not. Oh yeah, it is my laser pointer. Oh, there we go. Yeah, so this is the field of view right here. And we just looked at the Cygnus constellation over and over again. Here's the field of view zoomed in with the actual image, 10 degrees by 10 degrees. And I would like to show you the data for one representative star, Kepler 10. I'm going to be showing some actual scientific graphs, so I hope that's okay. This is the brightness of the star over here, and here is time. This is 100 days, 150 days, 200, 250, 300 days. And notice that the brightness here has the average brightness of the star at 1. So this is the average brightness, and here's 0.9995 of 1. So the Kepler telescope could measure the brightness of stars so accurately that we have an uncertainty, an error, of only 0.0001. So that was very, very good. If you look carefully, you can see a planet in the data. Monsieur, s'il vous plaît. So we have data here, and you see there's some dimming right here, and here, and here, and here. There's an actual planet that you can see with your eyes in the data. It's quite amazing, and here they are. You see how the star dims over and over and over again? I'll go back. It's amazing that you can see a planet orbiting the star, blocking the starlight over and over again. Also, you can tell that this is a small planet. How do you know? Well, the amount of dimming is very slight, 0.0005. So this is a planet that only blocks a tiny fraction of the light of the star, so it's much, much smaller than the star. And you can tell how long it takes the planet to go around the star, the orbital period. It's about 45 days, because from one dimming to the next, to the next, to the next, those dimmings are separated by 45 days. So you know a lot about this planet. You know its size, and you know the orbital period. And of course, the orbital period tells you how far the planet is from the star. So you learn a lot from just these data. But there's more. You can actually see a second planet if you look carefully. And I will show you the second planet by zooming in on these data right there. I will zoom in on that little tiny piece of data, and here's the zoom. There's one of the dimmings you already saw, but now do you see a second planet in there? and here and here and here. So you can see with your own eyes a second planet orbiting this star, and it's even smaller. It's right there. You see the red dashed lines? So that is a second planet, and in fact, you can see a third planet and a fourth planet. Notice that the second planet is smaller because the amount of dimming is less, and this planet only takes about 18 hours to go around the star. Less than 1 day, 0.84 days. So this is a remarkable planet, close in and very small, and you can calculate on a piece of paper the size of this planet, and it's about the size of the Earth. Here I've taken that graph and folded it over and over and over again, and so you see the dimming of the star only every 0.83 days, but the amount of dimming is very small. So small that this planet is 40% bigger than the Earth. I think all of you can see that with this telescope in space, Kepler, we can detect planets the size of the Earth. It's quite amazing, and learn how far they are from the star. Here's what we think the planet looks like. I'll remind you, we do not have a picture of the planet at all. No photo of the planet. But we think it looks like this. Here's the star, and then there's the planet right in close, blocking some of the starlight to dim the brightness. Now, I would like to tell you a little more about the science of these planets. We know the size, the amount of dimming tells us the size is about 40% bigger than the Earth. That's fine. But we would like to know, is this planet rocky like the Earth, or is it gaseous, made out of gas, like Jupiter and Saturn and the Sun? And to determine this, we need to know the density of the planet. What is the density? Well, to determine the density, we need to measure the mass of the planet, because we already know the volume of the planet, but if we knew the mass divided by volume is density, right? So we are going to try to measure the mass. And the way we do that is very clever. We watch the star, and as the planet goes around the star gets yanked on by the gravity of the planet. So the planet goes around, but the star gets jerked around, and if you can then just measure the motion of the star, then you can determine what the mass of the planet must be to cause that gravitational pull on the star. So we actually watch the star to learn the mass of the planet. And of course you use Newton's laws of physics that you learned in high school. But let me show you how you measure the motion of the star. It's quite interesting. We use one of the world's largest telescopes. This is called the Kepler telescope. It's located in Hawaii, high atop a hopefully dormant volcano. And so we measure the Doppler effect of the light. And the way we measure the Doppler effect is with a spectrometer at the back of this telescope. By the way, what is the Doppler effect? I think all of you know what the Doppler effect is, but let me remind you. When a fast car goes driving by, you hear the sound of the car change. You hear eeeeow. So you can tell from the sound how fast the car is going from the Doppler effect of sound. And we measure the Doppler effect of light from the star. Same exact physics. So we use this spectrometer spread the light out into all of its colors, blue, green, yellow, red, all of the wavelengths of light, and we look for the Doppler effect. This is the way the spectrometer looks. We get the spectrum at the very back, way over there on the right. And this is what the spectrum looks like. Every star looks like this, and we watch for the Doppler shift of the frequencies of the wavelengths of light, just like we could hear the frequencies of sound change when the car goes by. And with that, we measure the motion of the star due to the planet pulling gravitationally on the star. So that's the idea. And when we do that, we get a graph shown in the bottom right here, and you can see that the velocity of the star really does change, and it goes up and down. I'm going to get a new laser pointer. Hang on just a second. Luckily, I brought 2 laser pointers. Let's see if this one works. I got it. Oh yeah, that's much better, right? So here's the velocity of the star from the Doppler effect. And by the way, you can see the star changes its velocity. And that's because the planet is pulling gravitationally on the star. Very simple. And that tells us the mass of the planet. And then you know how to calculate density. It's the mass of the planet divided by the volume. By the way, do you know the formula for the volume of a planet if you know the radius? What's the formula for the volume of a sphere? I'm not asking you in the front. Who knows the equation for the volume of a sphere if you know the radius? Lots of arguments. The equation is the volume of a sphere is 4/3 pi r cubed. 4/3 pi r cubed, right? Okay, so now we know the density of the planet. Notice the density is 8.8 grams per cubic centimeter. Does anybody know the density of water? I'm not asking you. Yes, it's 1. So this is a planet that is much more dense than water, and therefore it's a rock. This is a rocky planet. Isn't that amazing? We don't have a picture of the planet. We don't know anything about what it looks like, but we can determine the radius, the mass, and the density, and therefore conclude it's a big rock like the Earth. This is what we think it looks like. This is an artist's rendering. And of course, again, we do not see the planet. We only see the star, and yet, look at all of the information we got about the planet despite not even seeing it. This is a hallmark of modern science. In modern science, you make measurements and you can infer the existence and the properties of an object without even seeing it. Like an electron. None of you has ever seen a picture of an electron, but you all know that electrons exist. Same idea. Very powerful. And I am going to try to go forward here. I need a little help, I think. I can't go forward for some reason. Let's see why. Yeah,
The movie?
yeah, it's not, I don't want the movie, I just, oh, there we go. Ah, perfect. Yeah, thank you. Merci. Merci bien. So, as you might imagine, we have used the same technique to find other planets. Here's 2 more planets. They are the size of the Earth. They orbit farther from the star, 122 days 267 days. These are planets like the Earth that takes 365 days to go around the sun. Here's what they look like, we think. 5 planets, they orbit that star. And then here's another artist's rendering. We don't have a real picture, a real photo. There's an artist's rendering. Here's another planet we found. Notice that the planets that are far from the star, here's the star, and the planet is here in the green region. That's called the habitable zone of a star. It's a distance far enough from the star so that the temperature is about 20 or 30 degrees Celsius, so that the water would not be in the form of ice, not in the form of steam, but at a temperature that makes it liquid. And of course, liquid water is the most important ingredient for biology. So that's a very exciting thing, that we are finding Earth-sized planets that are warm enough to have water in liquid form. Now, hang on. This looks like a complicated graph, but it's actually a beautiful graph. I will walk you through it. This is the size of the planets that we have found. Size of the Earth, 4 times the size of the Earth, 10 times the size of the Earth. And here's the orbital period. 1 day, 4 days, 10 days, 50 days, 100 days. And every planet gets 1 dot. Look at all the planets we found with the Kepler telescope. And what's amazing is many of the planets have a size between the size of the Earth and 4 times the size of the Earth. This is remarkable because our own solar system doesn't have any planets in that size range. So these are planets a little bigger than the Earth, but we've never seen planets like these before. And of course, many of them are in the habitable zone, but you might wonder, what are these planets like? They're not just like the Earth because they're bigger than the Earth. Why would a rocky planet be bigger than the Earth? What could make an Earth-like planet a little bit bigger? Well, one possibility is that there's a little water and an atmosphere, and that might make the planet 50% bigger than the Earth. What about a planet twice the size of the Earth? Add more atmosphere, maybe a little more water. What about 3 times the size of the Earth? Even bigger atmosphere, and 4 times. So there might be Earth-like planets that have thicker and thicker atmospheres, and those atmospheres make the planet appear larger as they go in front of the star, blocking the starlight. We would like to know how common Earth-like planets are. And the occurrence rate, or the frequency of planets, is simply the number of planets we found divided by the number of stars that we observed. And it turns out we can measure that very nicely. And here's the answer. This is a complicated graph too, but hang with it, it's not that bad. This is the fraction of stars that have planets. That's the occurrence rate of planets. The fraction of stars with planets versus the planet's size. 1 Earth radius, 2 Earth radii, 4, 8, and so on. Notice something remarkable. Look at all of the planets there are that are the size of the Earth and a little bit bigger than the Earth. 1.0, 1.4, 2.0. Most of the planets in the universe are approximately the size of our Earth. Most of them are probably rocky, big rocky core, some amount of water, and some amount of atmosphere. So this is amazing. And look at the number, 12% and 14% right there. Something like 26% of all the stars that you see in the night sky when you go out at night and you look up at the stars, 1 out of 4 or 1 out of 5 of those stars has an Earth-sized planet orbiting. Remarkable. A huge number of Earths. So this is the final conclusion about this. If you look at 20 stars in the night sky, on average, 4 or 5 of them will have a planet, and those planets are near the habitable zone. The temperature is not too cold, not too hot, but just right for liquid water. So you might ask, wait a minute, if I look up into the night sky, I see lots of stars, some are near, some are far. How far away is the nearest Earth-like planet? How many light years away? Well, light years are difficult to conceive of, so I would like to do an experiment, build a model of the Milky Way. I would like to imagine that the country of Algeria is the same size as the Milky Way. Here's an expanded Algeria. Imagine if you could expand Algeria to be the size of the Milky Way galaxy. Our Milky Way galaxy, of course, has 200 billion stars, but here's Algeria. And of course, we are here in Batagne, right there, in the Milky Way. And you might ask, how far away is the nearest Earth-like planet? And the answer, 5 kilometers away. You can get on your bicycle and ride your bicycle 5 kilometers to find the nearest Earth. Let me show you a zoom of how far away the nearest Earth is. There's Batagne, there's Kepler, and the nearest planet is right next door. So our galaxy is just filled with Earth-like planets. They're very nearby. And if you then summarize, you can see that out of our galaxy that has 200 billion stars, 1 out of 5 of them has an Earth-like planet. That's 40 billion Earth-like planets just within our Milky Way galaxy alone. And our Milky Way galaxy, of course, is just one galaxy out of 100 billion galaxies in the universe. So just within our Milky Way galaxy alone, look at all of the opportunities for biology. Amazing. Maybe there are some agronomy classes or chemistry classes being taught on the Earth-like planets on those around those stars. Now, I would like to finish my talk today with a topic about which I know zero. So if you will let me talk about something that I am ignorant about, that I'm stupid, that I don't know anything, please let me do that for 5 minutes. And the reason I say I don't know anything is I would like to ask the question, what is the probability of intelligent life within our Milky Way galaxy? Could there be other technological civilizations, vast array, many civilizations that are smart? Well, you can do the calculation. Let me walk you through it. Remember, I said 200 billion stars in the galaxy, our galaxy. 20% have habitable planets. Multiply 20% times 200 billion, 40 billion planets. I already said that. You might ask, what fraction of those planets forms intelligent life? How common, if you throw the dice, how common does the biology lead to intelligent life? Well, the most pessimistic answer I ever heard was intelligent life is 1 in a million. Maybe you need 1 million habitable planets, and only 1 out of a million gives you intelligent life. Well, if that's true, 1 out of a million, but you have 40 billion habitable planets, that means there must be thousands of civilizations, thousands of advanced civilizations just within our Milky Way galaxy. Why do I say advanced? Well, because we humans invented the radio 100 years ago. We are just a little baby civilization, a baby technology. But other civilizations might have started their technology 1,000 years ago or 1,000,000 years ago. So they would be advanced. We can't even imagine what their phones look like and the power of their phones because they're so advanced. So we have a prediction. The prediction is when you look up into the night sky, it's filled with advanced civilizations. Civilizations of very intelligent species that have technology far beyond what we imagine. Here is the prediction. The prediction is, like a science fiction movie, there must be spaceships and colonies and interstellar trade that we can't even imagine, but it's very busy. That's the prediction. When you look up into the night sky, do you see spaceships of the advanced civilizations? No. No. What, only? Yeah, right. So it's wrong. Something is not right. We have made a mistake. Because the universe, our galaxy, is not filled with advanced civilizations. We don't see the spaceships. Even with our powerful telescopes, we have never once seen an alien. We don't see alien spaceships. They don't crash land in Alger and say, I am here to meet the new president, or the old president. So something is wrong. We've made a mistake, and I would like to talk about, for the last 3 minutes, why or how we made a mistake. We do not see the advanced civilizations. Did we overestimate the probability of intelligent life? Where did we go wrong in our thinking? We made a mistake. So I would like to tell you some reasons. There are some explanations for why our galaxy is not filled with intelligent life. Maybe. And here are 3 possible reasons. First, our Earth is more special, maybe, than you realize. Our Earth has water delivered by asteroids and comets. That's why we have oceans, lakes, and rivers. But we only got this much water. The Earth only has a drop of water. It fills the oceans. That's wonderful. But suppose most Earth-like planets get less water, like here. Our Earth only has 0.06% water. What if our Earth had only received 0.03% water? Well, then the water would go into the interior of the Earth, the center of the Earth, and there would be no oceans at all. Most Earth-like planets might be like the Sahara Desert. Maybe. Alternatively, maybe most Earth-like planets receive twice as much water as the Earth did. In that case, the planets would be completely covered by water. If our Earth had twice as much water, the continents would be covered by water. There'd be no land, no dry land at all. And you can see that developing computers and pianos and buildings would be very difficult if we were completely underwater all the time. So maybe the lack of intelligent life in the galaxy is because our Earth is a special Earth-like planet with just the right amount of water. Another possibility for the lack of intelligent life is maybe on most planets you end up with bacteria and plants and animals, but maybe the animals never become smart. After all, the dinosaurs were on the Earth for 200 million years, and during the 200 million years, none of them ever learned how to build a computer or to play the violin. So both technology and even art was impossible for the dinosaurs. Why? Because the dinosaurs have tiny brains. They have brains that are bird brains. In fact, birds are dinosaurs. So it's possible that most Earth-like planets have life, but not intelligent life. And then finally, it's possible that in our Milky Way galaxy, civilizations do come up, they arise, they're born, and maybe there would be 1,000 civilizations, but the technology they develop destroys them. And I think everybody here knows that our own human technology could destroy us with nuclear weapons or synthetic biology, viruses, something like COVID-19 times 10. And so maybe even artificial intelligence is dangerous. So we have ways that our own technology could cause our existence to be very short, maybe another 100 years or another 1,000 years. That would be very, very short compared to the lifetime of the universe. So those are reasons that maybe advanced life, technological life, is rare. So I'll finish by saying the great effort now by my research team is to detect extraterrestrial intelligence. We are looking with radio telescopes, with optical telescopes. I just finished building an ultraviolet telescope. We're looking for radio wave transmissions, laser beams, ultraviolet light. The fiber optics would be in lasers to build a galactic internet. So we're looking for that galactic internet. Maybe they have a big laser system in the Milky Way galaxy. Maybe there's a World Wide Web, except it would be a galaxy-wide web, where they send pictures. They have Instagram and TikTok and Facebook, but it's the galactic internet and Facebook. And so they would send all of their information by laser beams. So that's the possibility. So I will finish with some conclusions. We are very, very lucky. We are lucky because for the first time, we know there are Earth-sized planets. We know that many of them are rocky, like the Earth. We know that many of them have a temperature that's just right for liquid water, the habitable zone. So liquid water could cause the biochemistry of life. And finally, our big challenge now is to find any evidence of that life, especially intelligent life. So I'll stop there. Thank you.
Thank you. Thank you, Professor Jeffrey, for that insightful presentation. We truly appreciate the time and the effort you put on the presentation to share your expertise with us today. And now I open the floor for the audience to ask questions. So please feel free to ask any questions you may have.
You want me to point them out?
Yes, I will point them. Yeah.
Okay, you point. Take yours first. Go ahead. You need it.
Questions? Do you have questions?
Yeah, there's lots of hands over here. You want this?
Yes.
Okay.
But we can maybe this.
Oh.
They do have.
So, I will repeat the question. She said she has many questions, but she would like to ask what is the most exciting discovery we have done. And I have to say, I didn't mention this. We started, my group, I started as a professor working by myself, all by myself, in 1983. And I know that's a long time ago, but when we started, when I started, I thought we would never find any planets. People told me I was crazy, fool. And they said, you will never find planets, stop trying. And I kept trying, and then I acquired one student to help me and another student. And eventually in 1995, we found our first planets. So in some way, that was the most exciting. We never thought we would succeed. And to find those first planets was truly amazing. We wondered whether the universe perhaps had 0 planets. Maybe our solar system is special. But it turns out not to be true. We found the first planets in 1995, and that was very, very exciting. The second most exciting was to find Earth-sized planets, and that came later. So both of those were exciting.
Your estimation of the number of planets that are habitable zones is about 20%. But the example also, but perhaps that number can be enlarged by a significant factor by taking into account stars which do not cross our
I know exactly. So this is a brilliant question. Let me tell you his question. Very, very smart. The technique we use to detect Earth-sized planets is that the planet must be in an orbit that just happens to be aligned with your telescope. So you are the telescope, and the planet must just go in front of the star. What if instead, he said, what if the planet orbits like this, in an inclination, or maybe like this, or maybe like this? Then the planet will not block the starlight, and we will not see the planet. Indeed, it is absolutely true. We missed more planets than we found, because the orbits were tilted and the starlight was never blocked. So what I did not say is that we make a correction factor. It's mathematical, it's simple spherical geometry. You can ask, given all of the planets we did detect, because the orbital plane is edge-on, how many planets must there be that are inclined 20 degrees, 30 degrees, 40 degrees, and so on? And you do a little mathematical correction factor. to account. So the numbers I gave had that correction factor in. And it's a big factor. It's a factor of 10. So we only detect 10% of the planets that are actually there. You want to come up to the front? Okay, these are two excellent questions. Thank you very much for those questions. I will answer her second question first. The second question was, there's a lot of interest in searching for life on Mars. And of course, Mars is in our solar system. It orbits the sun farther out than the Earth. And Mars is wonderful because it's very nearby. As we all know, it is possible to send a spaceship from the Earth to go to Mars. It will take about 9 months, but we can go. We humans have already sent robots. The United States sends robots, China, Russia, I think, India. Yeah, so it's not hard to go to the moon, and nor is it difficult to go to Mars. And someday we humans will go there. The interest is this. You know, Mars has a very thin atmosphere. It's only 1% of the density of the Earth's atmosphere. It's also very cold, sub-freezing. Every day is freezing on Mars. So Mars is an environment worse than the Antarctic because there's no atmosphere and it's cold. Still, it would be wonderful to go, and here's the lovely thing. The surface of Mars has no water, no liquid water, but there is ice, water ice, and carbon dioxide ice. Underneath the surface of Mars, where the pressure is higher and higher and higher when you dig down, there certainly must be water, aquifers. So there is liquid water, and there could be bacteria, maybe even more advanced life, in the water under the surface of Mars. So a very exciting reason to go to Mars is to dig under the surface and look to see is there any sign of life that was there as fossils now, or maybe still there. The other question really quickly is, how about we humans traveling to the other planets? Around other stars, right? And I can tell you something depressing. It's very, very difficult to travel to even the nearest stars. The amount of energy required, if you remember from high school, the equation for kinetic energy is 1/2 times the mass times the velocity squared. So if you take your mass and the velocity you need to go to another star, it's an enormous amount of energy. So going to the stars will be extremely difficult, if not impossible. You want to come up? I'll get you next.
Hello, first of all, thank you so much for coming here. This is such an interesting topic. Astronomy is so filled with questions. And my question is about this awesome research you did. You said that you had no possibility to capture the planets that you thought that habitable. My question is if this
Yes.
How do you know?
Yes. So this is a very good question. I spoke a lot about Earth-sized planets, but we also found much larger planets, planets the size of Jupiter. Jupiter is 10 times bigger than the Earth in size and 1,000 times more massive. So the question is, can we use a powerful telescope like the Hubble telescope or the James Webb Space Telescope and look at those stars, and can we get a photograph, get a photo of the Jupiter-sized planets at least? And here's the problem. The answer is yes, a little bit. The problem is the stars are very bright, very high luminosity, but the planets are dark. So when you look at a star with a planet, you cannot see the planet because it does not generate any energy, and therefore it does not emit any light. So planets are difficult to see, maybe by reflected light, but it's very hard. There are a few planets that have been directly detected, giant gas Jupiter-like planets, a few. I think I should get some over on this side for a second. Come on up. Oh, yeah. If you want to ask about go ahead.
Good morning, Mr. Marcy. I'm very happy to be here today to listen to your great experience. Well, I have two questions for you, sir. First one, like any astronomer, you may face challenges during your researches, such as finding and using technologies that may not have been advanced enough in the 90s and now. So, how did you overcome all these challenges and become one of the great scientists in the United States of America? The second one, we have many amazing discoveries related to exoplanets. Perhaps the most important among them is discovering the planet HT 2170140E, or known as 51 Pegasi B, which orbits a star similar to the Sun. Based on this, is there any possibility of a system similar to the solar system? I mean, planets we can live on and they have all the conditions of life, like water, atmosphere, and the source of energy, like chemical ones. And they orbit regularly around a certain star, and we can move on it in the future. Thank you.
Yeah. Okay, there were several questions there. The first one is really an important, profound question, and that is the challenge that we face, all of us, when we try to do research, is that you need equipment, and maybe you need funding to pay your collaborators. They need money for food, and they need a job. And so how do you get the money for a telescope, for your computers? And in the United States, this is a serious challenge. When you try to do research, one of the activities that's very important is simply acquiring the money. And it's unfortunate, but it's just the reality, because telescopes are expensive. So as a senior scientist like myself, acquiring money is probably the most important task. And then, of course, when you have some money, you need to be creative. So the one piece of advice I would give all of you is stay creative, think out of the box, come up with new ideas. Whether you're a chemist, a biologist, you're studying agronomy, you're doing physics, try to think of new ideas that nobody else has thought of. And I'll just answer your other questions real quickly. First of all, the first planet ever found was 51 Pegasi b, and I did not find that planet. Michel Mayor and Didier Queloz à Genève in Switzerland found that planet, and we quickly confirmed it. So, we were following in their footsteps. And there were other planets we found very, very quickly right afterwards. So I'll stop at that point. We can talk later.
I have a question.
I think there's only time for 2 or 3 more questions. Do you agree? Yeah. So I'll do you first, and then I'll try to get you over there. The 2 of you. Yeah.
I have two questions.
Okay.
The question is what if the life we are looking for is not subject to the sun, world that keeps alive on the surface of this planet? As you know, there are many bacteria that are able to live in difficulty conditions. Perhaps they do not even need water to live.
Are you asking about life that lives underground? Life living in space rather than on a planet. Yes, this is a good question. It's possible there's life that lives in space. Maybe some life lives in the large atmospheres of planets. So we need to be aware that there could be life that's very different from the life on the Earth. Maybe life that doesn't depend on liquid water. Maybe life that doesn't depend on carbon atoms, and so on. So, yes. Vous pouvez parler en français, n'est-ce pas? Did you understand that? Arabic. Ask in Arabic. Try again in Arabic. She will translate. En français. Okay. Thank you.
I really conveyed this information. So my question might be stupid.
No, it's not stupid.
In 3 years ago, I saw 3 balls in the sky at like the box. These 2 in here and 1 is in the up. So and something this battery.
Can I repeat? You saw 3 lights, 2 lights, and then 1 light up. Balls, 3 balls. White balls. Okay, this is a very interesting question, and I thank you for that question. He said he saw, was it at night? I think at night. He saw 3 balls, white balls. 1 ball that was white, another one, and then a 3rd ball that was white. What were they? And the answer is, I don't know. But many people see strange things in the Earth's atmosphere. They see strange things at night. Some people call those UFOs. Some people call them UAPs. But there are strange things that you see at night, and some of them we simply do not have an explanation. So many people are interested in studying these unidentified flying objects.
Thank you very much for giving me this chance. Okay, I think I have no questions today, but I need to say that you have a very beautiful way to explain the most complicated things and make us very clear to us. That's very good for us. And I think that's a huge work, and I hope you achieve the most wonderful and fantastic
two more, that's it.
Two more questions and we close the session.
Okay, thank you, Professor, for the talk. Yeah, I have a question regarding the atmosphere surrounding those like planets.
Yeah.
You're talking about water, yes, but what about atmosphere? Do you have any idea about the composition of the atmosphere surrounding those planets?
Yes. Yes, so it's a very, very good question. It's a topic of current research. The question is, these planets that have atmospheres, do we have some idea of the chemical composition of the atmospheres? And there's two answers to this, theoretical and observational. Theoretically, the most common atoms in the universe are hydrogen and helium. They dominate the composition of the sun and other stars, and Jupiter and Saturn and Neptune and Uranus, their thick atmospheres, hydrogen and helium, mostly. So the first guess, theoretically, for these other planets is they have thick atmospheres composed of hydrogen and helium. Now, in addition, there's probably common molecules, simple molecules, carbon dioxide, maybe methane, CN, CO, carbon monoxide, any molecule that has carbon, nitrogen, oxygen, or hydrogen, those four atoms, you can combine it and make a common molecule. So certainly the planets have some of those molecules above. And the second answer to your question is, with the James Webb Space Telescope, people are watching the planet go in front of the star, and some of the starlight goes through the atmosphere onto the Earth. So you can see the absorption of the molecules of the light, absorption by the molecules of the light, and literally get a spectrum and identify sodium as well as carbon monoxide, carbon dioxide, and so on. So people are observationally detecting the molecules in the atmosphere.
Hello, sir. My name is Bajamma. I'm a first-year student at Milky Way High School. First, I thank my director for that, and I thank you too for your time. I just have a simple question. You mentioned before they are advanced civilizations, right? I just want to know why they don't come to visit us.
Yes. So this is a profound question. Why don't the other intelligent species in the galaxy, why don't they visit? And the reason this is such an important question is that the advanced civilizations out there, if there are any, have plenty of time. They could come here in a spaceship very slowly, or they could send a robotic spaceship. Maybe they don't come themselves, but they send a robot or a spacecraft that has a computer on board. We don't see those either. So it's very profound that we do not see evidence in the sky, but we also, when we go to the Mediterranean coast, we don't see resort hotels built by the aliens. Why didn't the aliens build, hotels on the Mediterranean, a beautiful place for the aliens to visit? And I'm not entirely being humorous. It's a serious question. And I would argue, I would answer your question by saying the absence, the lack of advanced civilizations here on the Earth and the Moon and Mars is a very good indicator that there are very few advanced civilizations. Because if there were lots of them, they would already be here.
Thank you very much, sir.
Okay, this is the last question. It better be a good one, too.
Hi, sir. I'm Miriam. So I'm a student at Milky Way. I want to say our
us do.
But in this question, I want just your opinion. Just your opinion. Why we are not allowed to go to the South Pole, the ice, at the same time that if there are many things to explore more than the North Pole.
Oh. Well, I think the question is, should we go to the South Pole rather than the North Pole? Yeah, there's a very good answer here, of course. You know, the South Pole has land. It's an actual continent. So the ice is sitting several kilometers thick on land in the Antarctic. In contrast, the North Pole, there's no land. The ice is floating because of its low density on the ocean. So the Antarctic is a place you can build scientific equipment, you could put laboratories, telescopes, study the life forms there. And so the Antarctic is a more permanent place to put your laboratory equipment. There are people who go to the North Pole too, but unfortunately the ice melts some of the time. So as global warming continues, the North Pole will become just liquid water someday soon, probably in 50 years.
Thank you